The next question is based on how functions form a linear vector space. So before writing down the question, let us look at how we are defining the functions and how these functions will be forming a linear vector space. So the example given in the book is, let us say we have functions fx defined in the interval 0 to L, where L is some finite real number. So our function is basically defined on a finite domain. This is finite, this is not infinite. X is not going from minus infinity to plus infinity. So we have a finite domain for the function f of x, and for this we are defining the scalar multiplication. How are we defining the scalar multiplication? A times f of x, where a is a real number. So this is the scalar multiplication. And then we define addition. What is the addition? It is pointwise additions, meaning that if we have two functions, let's say two functions f and g. So what is happening is these functions have a certain value at a given point x. So let's say we have two functions and then we have a given point x. So we define the addition in a way that f of x plus gx gives us the value of the sum of these two functions at a given point x. So we have two functions f and g, then at a given point x, this is how we define the sum. So we have scalar multiplication, we have addition. So from these we will see that the axioms are being verified. Then what is the null vector in this case? So the null vector in this case will be some null function. What is that? This function is basically 0 everywhere on the domain. That is, f of x is equal to 0. This is our null function. Then what else do we need? We need the additive inverse. We need additive inverse. So if we have so basically a function f, then the additive inverse is minus f. And how is that? So let us look at this null function. So the null function says that f of x is equal to 0. Now if we consider some function, let's say g, so g of x plus f of x is what? G of x plus 0, because we are taking this null vector, null function. So this is g of x, because adding 0 to something gives us that number itself. So this means that f(x) equal to 0 is the null function. So, and from the uniqueness of the null vector, we know that if we have found one null vector, then that indeed is the unique null vector. And then let's look at inverse, the additive inverse. So if we have a function f of x, and if we add minus f of x to it, then what do we get? So these are numbers, right? F of x will be some number minus f of x will be the negative of that number. So this, adding these two would give us 0. And 0 is what? This is the null function. So 0 is null. So this implies that minus fx is indeed the inverse of f of x. And again, from the uniqueness of inverse, we know that if we have found one inverse, then that indeed is the unique inverse for that particular function of particular vector. So from this we see that if we have functions defined on a limited domain, on some fixed domain which is not extending up to infinity, and if we define the scalar multiplication and addition as pointwise addition, then we see that these functions defined in this interval do indeed form a linear vector space, where we have the null function or the null vector, which is a function which takes the value 0 at each and every point in this given domain, and the additive inverse is a function which takes the negative of the values of that function. So with this definition of functions defined on a domain, we now move to the question that we have at hand. So the question, this is exercise 1.1.3. So this question is based on functions defined on this kind of a domain and whether or not certain class of these functions form a vector space. So the question says, do functions that vanish at the endpoints, what are the endpoints of this domain? X equal to 0 and x equal to L form a vector space. So do such functions which are vanishing at endpoints form a vector space? This is the first part. Then the next one is, how about periodic functions? So periodic functions meaning that they will have same value at the endpoint. Periodic functions obeying f0 equal to fl, but this is not vanishing. So over here, see, in the first part we say that these functions are vanishing at at the endpoints. So at x equal to 0 and x equal to L, these functions will have the value 0. The next part is periodic functions, wherein the function value at x equal to 0 and x equal to L is the same constant number. Then the next, there is another part. How about functions that obey f0 equal to 4, and then we need to specify which of these functions form a linear vector space, which of these functions do not form a linear vector space, and then we need to give reasons for our arguments. If the functions do not qualify, list the things that go wrong. So basically we need to justify our claims, why we are saying that certain functions will form a vector space, why certain functions will not form a vector space. So let us solve this question. Let us look at the first part. So the first part says that functions are vanishing at the endpoints. What that means is that, so let's say for the first part, it means that f at 0 is the same as f at L, which is 0. So does this form a linear vector space? Well, to check that, we need to look at those axioms, those 8 axioms we saw in the very first video, and then we need to see whether this class of functions follows those 8 axioms or not. Just to revise, I will show those 8 axioms once again. So once we have the definition for the linear vector space as a collection of such objects for which we define the addition as this vector sum, and then we need to have a scalar multiplication, and then we have these 8 axioms, first one being the closure property, then the next 2 are based on scalar multiplication having the distributive property, so it is distributive in vectors, distributive in the scalars. Then scalar multiplication is also associative. Then it says that addition is commutative as well as addition is associative. And then the null vector needs to exist as well as the additive inverse needs to exist. So these are the 8 axioms. If all of these 8 axioms are true for a given collection of these objects called vectors, then these objects will form what is called a linear vector space. So basically, to show that a group of objects or entities are forming a linear vector space, we need to see that each of these 8 axioms are being obeyed by those entities. So let us come back to our question and let us see if these class of functions obey these axioms that we have or not. Sorry about this. Yes. So the first one is closure. Closure meaning if we have a function f and another function g, then f of x plus g of then it basically means that f plus g is also another function existing in this set. So is this true? Fine, let us see if this is true or not, if closure is being satisfied or not. So if we have f of x plus g of x, let us call f plus g is equal to some other function h. So f of x plus g of x will be some h of x. This is by the definition over here, definition of addition of two functions that we defined. It is a pointwise addition of two functions. Now do these functions follow this property that we have defined? Well, of course, yes. So why? Because f of 0 plus g of 0 is nothing but 0 plus 0, which is 0, and this will be is equal to h of 0, and this will also be equal to 0. So we know that this function is satisfying, the sum of these functions is satisfying this property that we have defined for us. Similarly, at the other endpoint, f of L plus g of L is equal to 0 plus 0 is equal to 0. This is h of L. So closure, that means we have closure property being satisfied. Next, we need to look at scalar multiplication. So scalar multiplication is distributive in the vectors. So that means if you have a scalar a and then we are having f of x plus g of x, this by the definition of the scalar multiplication that we have, this scalar multiplication over here, this is defined. So this is nothing but a of fx plus a of gx. So we have scalar multiplication is distributive. distributive in vectors. Then the next axiom is about distributive nature of scalar multiplication in the scalars, that is a plus b of f of x is equal to a times f of x plus b times f of x. So this is scalar multiplication is distributive in scalars. So notice that these this f of x and g of x, these are numbers. So function is defined in a given domain. We have this domain 0 to L, and f of x is a number. So f of x is a number. X is also a number which is defined in this domain. So this number is in this domain. So each of these x and each of these f of x are numbers, and these numbers are real numbers. So these are real numbers. So when we say f of x plus g of x, so this is some real number plus another real number. And from real numbers, we know that real numbers are definitely distributive. So sorry, I wrote this spelling wrong over here. Not distribution, distributive. So this f of x is a number, g of x is a number. Similarly here, fx is a number, a is a number. All these are real numbers. And for real numbers, we know that the addition is, the multiplication with real numbers is distributive. So these two statements that I just made about scalar multiplication being distributive comes from the fact that real numbers have this property. So since real numbers have this property and these functions are taking real values, we see that these two properties are being satisfied. So the next property is the associativity of the scalar multiplication. So we have a times b of fx is equal to a b fx. This is the next property which says scalar multiplication is associative. Again, how do we make this claim? Based on the fact that all of these are real numbers. A is a real number, b is a real number, fx is also a real number, and real numbers are definitely, the multiplication of real numbers is definitely associative. Next comes properties for addition. Addition meaning f plus g should be equal to g plus f. This is addition being commutative. And is this true? Well, yes, if we have fx plus gx, this is indeed equal to gx plus fx for all the points x lying in that domain 0 to L. This is true for all points. This is a point-wise addition, and each of these numbers fx and gx are real numbers, and real numbers, the addition is commutative. So we have this, that addition is commutative. Next property is about addition being associative. So what does that say? That f plus g plus some another function, so we can group them in different manners like this. So this is showing that addition will be associative. How can we make this claim? Again, we will take some point x and we will do this pointwise addition. This is how the addition of functions is defined in our given example. And again, since all of these fx, gx and hx are real numbers, we can make this conclusion that addition is associative. Then it is about the null vector, or in this case the null function. So this we have defined earlier. We have defined our null function being fx equal to 0 at all the locations. Fx takes 0 value at all the points in 0 to L. This is our null vector. We saw this above, why this is a null vector. Then finally the last one is about the additive inverse. Additive inverse of f is minus f. This again we saw above. By this definition we see why this minus f is indeed the additive inverse of f. So in the first case, where the function takes the value 0 at endpoints, this function indeed forms a linear vector space, as we see, because all the 8 axioms are being satisfied. This function satisfies closure property, all the other properties. Does this class of function have a null vector? Yes, indeed it has this null vector which takes the value 0 everywhere. This does satisfy this condition that we have, because at x equal to 0, f0 is indeed 0. Similarly at x equal to L, f of L is 0. This function takes the value 0 everywhere. This is the null function, so it definitely takes the value 0 at the endpoints. Does the inverse exist? Yes, indeed it exists, because negative, so let's say at the endpoints, the endpoints are fixed. So at x equal to 0, does the inverse exist? Yes, it exists, because f of 0 is 0, and if we look at minus f of 0, that is also 0. So and if we add f of 0 plus minus f of 0, that is also 0. So this is because negative of 0 is also 0. 0 does not is like the inverse, additive inverse of itself. Similarly at the other endpoint, same thing. We have f of L equal to 0. The negative of f of L will also be 0, because minus 0 is same thing as 0. So this function has the null vector or the null function. It has the additive inverse. So this certain class of functions that we have indeed form a vector space. So the conclusion is that this forms a vector space. This is the conclusion that we draw for the first class of functions that we were given. Next let us look at the second class of functions. Second class of functions, how about periodic functions obeying f0 equal to f of L? Now this periodic functions, meaning the value at the endpoints are same, it's a constant, and this constant is non-zero, because for 0 we have already looked at this case 1. So let us take this to be some non-zero constant. So f0 equal to fl equal to some c which is not equal to 0. Now we need to see if this class of functions forms a linear vector space or not. For that, let us see if the inverse function exists or not. So for inverse, we will have minus f as the inverse of f. So minus f, let's say at x equal to 0, will be what? By the definition, it will be minus of f of 0, which is equal to minus of c. Now, minus of c is definitely, so this minus of c is at x equal to 0, and this definitely does not satisfy this condition. Why? Because minus c is not equal to c for a non-zero constant c. So we see that the inverse does not exist. Inverse does not exist. Let me repeat myself why I am saying the inverse does not exist. Because this function which takes some negative value, some different value at this x equal to 0, is not allowed by this definition that we have. From this definition, at x equal to 0, all functions should take the value c. Now clearly our inverse function is not taking that value c. Similarly, if we look at x equal to L, so minus f at x equal to L minus f of L, this is equal to minus c, which is not equal to c. Again, at x equal to L, all functions should take the value c by this definition that we have, this definition over here. So clearly our inverse function is not taking that value c. It is taking some other value. So this is not, so this inverse function is not a member of this class of functions. So the closure is not satisfied for this inverse function. That means this inverse does not exist in this set of functions that we have. So because the inverse is not existing, this set of function does not form a linear space. Sorry, we will write not a linear vector space. Why? Because the inverse does not exist. Similarly, let's look at the third class of functions defined, which says that f of 0 is equal to 4. So this is the question, that f of 0 equal to 4, does this class of functions form a linear vector space? Similar to the above example that we saw in number 2, we see that the inverse here also does not exist. Why? Because minus f at x equal to 0 is minus f of 0, which is equal to minus 4, which is clearly not equal to 4. So the function value at x equal to 0 should be equal to 4, but we are getting minus 4. So this particular class of function does not exist in this set. So that means the inverse function does not exist in this set of functions obeying the rule f of 0 equal to 4. So again we have that inverse does not exist. Since the inverse does not exist, that means this function is, this class of function is not a linear vector space. Not a linear vector space. space. Notice that in this example 2 and 3, so if f0 equal to fl equal to c, had this c been equal to 0, then this would have formed a vector space as we saw in this part 1, wherein f0 equal to fl equal to 0, this class does indeed form a vector space. But if that f0 equal to fl equal to some constant which is not equal to 0, then it does not form a vector space because the inverse does not exist. Now from this equation that we have, this relation that we have over here, you can clearly see that minus c will be equal to c if and only if this c equal to 0. That is, minus c equal to c if and only if c is equal to 0. Else it is not the same. Else the negative of number is not the same as the number itself. This is only true if that number is 0. So had this c been equal to 0, then this would have formed a linear vector space as we saw in the first part. But if this constant is not 0, then it does not form a linear vector space. So this is important. We need to see what the value of this constant is. For all non-zero values, it does not form a linear vector space. Only for this constant being equal to 0 do we get a linear vector space.